Yeah, I think this is it. All right. Here we have a line, the way we know it, okay? And this line is going to the point 0, 2. And it's also going through, there's a 3 here, and that's a 4 there. So that's 3, 4. So now we could work out the gradient of this line. The gradient n is 2 over 3. So this line has the equation 2 over 3x plus 2. Right? The gradient is 2 over 3 and the y-intercept is 2. And that's the way this line is described. And that's really the only way that we can describe this line. We can write this in a different way. We can say 3y equals 2x plus 6. But it's still the same line, described in the same way. Now, if we look at it from a perspective of vectors, what we do here is we start from the origin, our big reference point, and the first thing to do is from the origin is get on the line. And typically, we get on the line at the y-intercept, there. So that's our first vector there. Okay? And that would be the vector 0, 2. And then once we're on the line, we want to move along the line, in the direction of the line. And the direction of the line is sort of given by the gradient. It is the rise over the run, or in this case, the run and the rise, there. This direction vector is the vector 3, 2. So, adding to the 0, 2, going into the direction 3, 2. But the thing is, I need a parameter to do that. Because I don't want to do, I want to be able to go lots of vectors 3 or 2 in that direction, but I also want to be able to go the other way. And I want also to be able to go half, for instance, that distance. So what we would do typically is give this line a name. Maybe the line is called L. And then we need another parameter, and that parameter typically is t. And t is then any number. Okay? So if I make t1, t for time really, if I make t1, that means that from the origin I go to 0.2 and then I go in that direction. So I'll end up in the point 3.4. I'll end up there. But if I make t equals 2, then I'll end up in the point 6.8. Is that true? It is true, isn't it? 6.6. 6.6. And that is true. But I can make t -1 as well, which means I'm going the other way, and I'll end up in the point 0. -3, 0. See, so according to what I choose for t, I move along this line, which is very similar to according what I choose for x, I move along that line y, and I get the different points of the line. It's just another way of describing it. Okay? Now the good part of describing it in this way is that we have a choice. Because I now not necessarily have to go to this point here, to 0.2. Instead, I could choose, for instance, to go to another nice point, let's say this one here. Oh wow, that's a biggie. There. So I could choose this vector. And that vector gets me on the line as well. So, and then the direction of the line is the same. It's still that vector, which is still the vector 3, 2. But this is the vector -3, 0. See? Put a big fat line there. So how does my equation look then? Well, I can't call it L anymore, but I could call it, for instance, K, the line K. And the line K is made up of -3, 0. And then I can't use T anymore because I have already used T. So I'll use S, 3, 2. And in fact, line K is the same as line L. They are the same line. Exactly the same line. Which could only be described by y equals 2/3 x plus 2. This is the only way to describe it in ordinary sense. But in vector sense, this answer for L is just as good as this answer for K. Because it describes the same line. T and S are not the same thing though. If on this line I want to end up in that point there, S needs to be 2. Okay? Here T needs to be 1 to end up in 3, 4. So T is actually S take 1. So the big deal here is, in vector maths, you've got multiple ways to describe a line, and you're not bound anymore by the y-intercept. You just need any point on the line. Any point on the line will do, and then from there on you just move in the direction given. And that describes the line. And that goes for 2D and 3D.